The FS Storm is, and Storm is essential piece embedded to the cloud platform that Perlucid has developed for various applications. So agriculture is our test bed where we're testing this stuff, but we already have several other projects on the go where we'll be using this cloud framework and interface with potentially hundreds of thousands of devices. All right, so let me try and jump to the primary reason why we're probably here, because we need to be scalable when we write our applications. And what does scalable mean and how does it relate to availability? Well, apparently the two are related and really two sides of the same coin. Unless you can scale, you don't really have availability. So you really have to scale out, and that's where distributed part comes in. Once you are scaling out, that means that you're running on multiple machines, and you have to approach the problem solving completely differently compared to the way where you have a small environment that's perfectly connected and isolated from possible interruptions. So how do we calculate availability? Well, it turns out it's a product of availability of all your components. So if your database is busy, that means your entire system is not available. So if you're looking for 99 percentile availability, you're never going to get it if there is a chance that your database is going to time out. So what does the distributed computing landscape look like? And there are many options out there, from gRPC and actors to event stream processing and batch processing. One thing to differentiate them is the sort of data freshness that they're dealing with. So in case of gRPC and actors, the data that you get back in case of distributed computation is very fresh. It's right away. You just got it. In case of batch processing, you're on completely opposite end of the spectrum. You accumulate a lot of data and then you start processing it across your computational cluster. And the event stream processing, which is what I'm going to talk about, is in the sweet spot, somewhere in the middle where it can satisfy a lot of problem domains. You don't get the data right away or as fast as you could with custom gRPC, but it's pretty fast. Often fast enough for majority of your needs. So one differentiation I want to really address in this presentation is ask versus tell, as I call it. Or pulling for data versus pushing the information out and let other parties deal with this update. So here's an example from my previous domain where Ian works now, which is probably oversimplified and mostly incorrect, but I'll describe this and what's in theory is going on here. We're trying to price a financial instrument, and the pricing is fairly involving. There's a lot of computation going on. It's a fairly large domain. And for simplicity's sake, we say that there's two input parameters into it. So we're looking for a price on a certain date, given certain risk parameter. And at some later date, we'll also identify that the risk can be modeled in different ways. So a model is another implicit parameter into the price calculation. So starting with the traditional development, we end up with lots of APIs, and we end up with a single stack with lots of methods calling each other. So how would we approach scaling out something like that? You can see I intentionally pointed out that it's just a fragment of a stack, that we're not calculating the price by itself, that it's part of a larger calculation. We're going to do something with those results, and there's something going on in the model retrieval space as well. All of that should give you an idea that this is a fairly complex process. It's going to take a while, and if we're pricing a portfolio of, say, 10,000 financial instruments, it's really going to take a while. So when we started it, when this product originally was developed, the use case was we're running it on a single machine. The user has that machine entirely to himself, and whatever resources and time that the program is spending is perfectly acceptable. So if they wait for 10 minutes to price a portfolio, it's fine. Now we're trying to scale this out and run this as a web application. So given this stack, how could we scale this out? Well, it turns out that it's really difficult. And there are several aspects to the scalability. One is how fast you can make the computations. But another one is how can you break the code base apart in such a way that your larger team, because it's a fairly complex domain, you need a large team, can coordinate their work. Turns out that when you consume your APIs directly, they're very fragile. You add another parameter, like I introduced the model here, and all of a sudden you have to make difficult decisions. Is that model implied? Is it coming as a default argument from somewhere? Or do we break the API and request that all the consumers have to pass it in? So what ends up happening in practice is that it's very difficult to make any sort of change once you build a system like that. Another distinct aspect is fault handling. With this sort of approach, what we usually do is handle an exception. So what's our story with regards to exceptions? Well, we just keep offloading that to our immediate consumer, let consumer deal with it. Essentially, we're not dealing with faults. Essentially, we're saying, I'm not going to deal with this, it's your problem, and it ends up being user's problem. If we failed somewhere, it's on the user to figure out what to do with it. And again, it may be okay if the user has perfect control of the environment, and they have to figure it out once. But once you're in a web environment, basically you can't tell user that, sorry, we're not available right now. Come back later. And another interesting problem that I tried to solve working in this sort of architecture was caching. Turns out it's really challenging to cache anything. So here you can see that I'm asking for a model. What's the typical problem with cache? Well, how do you know when you can expire it? Looking at the stack, how can you tell which layer in the stack controls the cache? Which layer controls the context? Which layer decides that it's okay to clear out the cache at this point? Turns out that all of these problems are really hard. So hopefully we can simplify this entire situation with events. And what are the events? Events represent summary of change, and usually they're self-contained and they're implemented via store and forward messaging. What does self-contained means? Means that the type of message perfectly describes the situation we're in as well as what has changed. So you can write highly precise logic around that because it gives you everything that you need. And one exception to the self-contained may be, actually not so much exception, but the self-contained is really a guideline, and in practice it often happens to be a range. How much do you include in the message? So if you're including risk parameters, well, you may end up with such a large message that your throughput will suffer. So typically it's a balancing act. You have to figure out what most of your consumer need and include that in the message, and sort of like in a star schema, include reference to other things that they may need down the road. So most of the data that related to that event you would include with the event itself, and include references as to where to find more information. The events are time relevant, not time sensitive. And what do I mean by that? When we're dealing with something like stored procedure call to the database, we have to specify what the timeout is. The busier the database, the more likely you're going to fault because you exceeded the timeout. So with event processing, there's no immediate caller. There's nobody waiting for someone to process this event. So all we want from the event is that they're sequentially ordered, which is what I mean by time relevant. You want things to happen one after another, but it doesn't matter how long it's going to take you to process these events. Events could be uniquely identifiable, and it's really handy for tracing and for correlation. So if you want to say that one event relates to another event, how do you figure that out? Because you don't have a call stack anymore. All you have is a piece of data going around. So you introduce correlation ID that uniquely identifies chains of conversation or chain of events that you can relate together. And another important aspect with messaging is idempotency. Idempotency is a weaker form of immutability when you want to have side effects, but you want to have them at most once. And that's where correlation ID may help as well. Because your events are uniquely identified, you can look whether you have handled this event already or not. If you did, you just let it go, like nothing happened. And here's what tell information flow would look like. Here we have components that produce events. In case of model update, we issue an event that says model updated. We include the information about the model, and we include the date when it has changed. If it's time to issue a new date, we could have some sort of date service that issues dates periodically. We can issue a new date event and subscribe all the interested parties that need to know that new date has started. As you can see, this results in 4 different stacks, completely independent. Very easy to test in isolation, very easy to parallelize because the events are self-contained. They include all the information pertaining to the change. You can compose those consumers at runtime as opposed to design time. That simplifies your preliminary analysis that you have to do in the domain before you can come up with a solution. It's less fragile because you can change the components independently. There's no API that you're going to break. The only thing that you have to conform to is a message format. As long as your consumers understand your message, there's no API to break.
What's the difference between a message format and an API, though? I mean, aren't they more or less the same thing? If you're saying in advance, this is how we're going to communicate.
Yes and no. Here's an example. If I'm introducing a new version of any of those components, for example, I introduced new model. And new models got new fields in the message. First of all, the message itself can be defined in such a way that the change that you're going to introduce is going to be additive. If it's not additive, that's still fine. Why? Because there's no immediate subscriber. There's no direct point-to-point communication between those components. The technical term is location transparency. When you don't know what's the other party that involved in the conversation, where the other party is, you just publish a message. You don't really know who that other party is. So let's say we introduce new model, and this RIS cannot handle that message anymore. It's not backwards compatible. What we can do is introduce another version of the RIS consumer that does consume these messages, and you can have 2 versions running in parallel. And absolutely nothing is broken. Your programs still compile. Your messages are still handled. But you now run in 2 versions in parallel.
So So what I'm seeing here is, first of all, you're talking about this is the TEL approach, right?
Yes.
Okay. And I can sort of see how caching becomes easier here because you're just pushing things out, and then whoever's listening to those kinds of messages can cache whatever results they want in response to that.
That's right.
Doesn't that create a massive amount of data, though? I'm thinking about the price at the end where all of that stuff's trickling down. If it starts caching all, I mean, I guess you can only keep n results and then ditch the rest, but...
So potentially there is more computation involved. If you remember the ask approach, basically you could skip through God knows how many changes before you decide to compute the price again. But what happens is that there's very little optimization you can do in that process. Whereas here, yes, you do more computation, but it's continuous. If you need faster speeds, well, you could make faster infrastructure. You could spin up more nodes that handle those events. And you can have consistent speed. As long as you're happy with the speed, it's going to be consistent throughout your entire week work. Whereas with full approach, you're going to have peak hours where you need 100 times worth of infrastructure, and you still can't meet the demand. Whereas here, you just continue processing them continuously. And what happens is there's no there is no work that's wasted. Every computation you do happened there for a reason. There was a change that you need to address. If you go back and look at the pool mechanism, basically there is no way to tell whether or not you're going to do the computation again. Like I said, you don't really have control over cache context. If you've written it to the disk, one of the parameters has changed underneath. How do you know that you need to recalculate? And I can tell you how my previous employer addressed it. They pushed the choice to the user. They said, you want to calculate this again? We don't know if anything changed, but you want to calculate it again? There's a checkbox for you.
Yeah. So the idea here is that you want to just pretty much get all of the prices for all of the products sort of in a database somewhere.
That's right.
You update that database as changes trickle in from the top.
That's right.
So so I guess here with the trade-off is that you've got a lot of stored results. While in the previous one, let's say they only wanted to get 2 results, you didn't compute them uselessly. But I see the advantage of what you're talking about. I just want to make sure I understood the trade-offs.
Yep, you're perfectly right.
Yeah. Okay.
So because event consumers have to have the life of their own in order to be available and handle that event, we have these different stacks. Every one of them is alive at all times and ready to accept the messages. If they're not ready to accept and handle the messages, well, we actually have a problem. So how do we package it in a way where the components have their own lifetimes? Well, we're going to have to come up with some sort of microservices. What defines a service in the first place? It's something that encapsulates business logic. Hopefully it can evolve independently as long as the service API remains the same, independently from other services that you have in your business domain. But what differentiates them from the library is that they control their context. They control their security context, they control their lifetime, they decide what sort of performance optimization they're going to do, if any. If they're going to have cache, it's going to be inside their process and inside their control. If they're going to have security and authentication, it's going to be implemented per service, according to the needs that the service has. Whereas with library, it's really up to somebody else's context to see what any of those things are going to look like. And microservices, a term has been hijacked by the Rest crowd, but essentially it's doing one thing well. And the only issues with that is that it turns out they introduce latency. The more smaller pieces in your infrastructure you have, the more time they spend in transit talking to each other instead of doing things that they used to do in a single call stack. Another thing is that now we have deployment and management overhead. We need to configure all those services. We need to deploy those services. We need to make sure that those services are running and meeting their SLAs. So more overhead on the infrastructure part. Here's an example from IIT Space. I have a thermostat that I can configure to trigger an alert if temperature crosses a certain threshold. I've got sensor events saying that the sensor is up, started receiving events from that sensor. I see the temperature updates coming from that sensor, and I have another management event, which is settings have been updated. So the user went and said, instead of 10 degrees alert trigger, I want to have 15 degrees alert trigger, or instead of 10 degrees Celsius, I want to have 10 degrees Fahrenheit. So user preferences have changed. So I've broken it down into events and something that should happen with them. So how would we build a system that addresses these requirements? When I worked with mass transit, which is an excellent .NET service bus, if you need to live entirely in .NET ecosystem, you get static verification for everything, and really nice tooling around it. So what I would have designed before would have been queues. So all of those handlers, event handlers, would have been implemented inside services, and they would be sending messages to each other over a persistent queue. Why persistent queue? Well, we want to make sure that we handle those events. And what it means is that we handle those events is that even if service is down at the moment, we want the fact that the event has been triggered persisted so that we can process this later. And this is what Twitter was doing. And they found out that latency between all those microservices is unacceptable. Every time you go into the queue, you're going to hit the disk, and the disk is really bottleneck these days. It's really hard to do things fast when you have to touch the disk. So what did they do? They wrote Storm. So the goals of Storm: maintain the reliability semantics of persistent queue. So they want to provide the same guarantees that persistent queues give you. If message has been issued, it's in the queue, we're guaranteed that we're processing it. But they want to avoid hitting the disk every time they go from microservice to microservice. So here's a simple concept that Storm has introduced: spouts that produce messages, bolts that consume them, and streams that transfer the messages from component to component. Spouts maintain the reliability semantics. It's really on the spout to decide whether or not the message has been processed according to the business requirements. And Storm helps to maintain this reliability semantics by building something called tuple tree. So every message that goes from component to component is called a tuple. And the tuple tree is something that you build up by meeting messages from one component to another and attaching one to another. And this attachment is called anchoring. So if this bolt produced new tuple that needs to be processed in order for original tuple to be acknowledged, you just attach new one to the existing tree, and the Storm makes sure that the entire tree has been acknowledged before it goes back and tells the spout that it's okay, this message has been processed. This way, the persistence happens only out here on the edge, on the very beginning. You write something from the queue, and from that moment on, it's entirely in memory. You can be really fast living in memory only. So the concepts: spouts, they're throttled by Storm. Unthrottled spouts are really, really counterproductive. What happens is that you can emit so much data into the rest of your topology that it's just boggled down processing all those messages. At some point, there's a sweet spot where you want to stop and let the things process before you go on. So Storm lets you throttle spouts. Streams could be default, unnamed, and you could name them. All of that is really to address this scenario when you have a spout that emits multiple tuples or tuples into multiple streams. Bolts. This is where processing happens. Bolts can consume tuples and arbitrarily emit them. There is no throttling on the bolts. They could sit there and collect 100 messages before you decide to emit another one from a bolt. And grouping or affinity of tuples within the stream. That has to do with the parallelism. You can specify how many bolts you want to run in parallel, or in fact any components, how many spouts you want to have running in parallel. But the grouping relates specifically to bolts. Sometimes it's important that certain messages go to specific instances of spouts. For example, all the even numbers go to one spout, or all the odd numbers go to another spout. And it's achieved through grouping. Grouping that lets you shuffle is default grouping in Storm, which means you don't care which instance of that component the messages are going to. It's just going to go round robin around them and handle to the first available. Fields lets you define sort of a key on a tuple. That's the only time when Storm really cares about your tuples. That's why they're called tuples, because ideally they don't have names or schemas. The only exception why Storm would care about the field names in your tuples is so that it could do grouping on something like a key. So how is that useful? Sometimes it's important to implement persistence from the same instance of a spout. Why? Because you could serialize your persistence that way. Another example is InMemory Join. If your bolt looks like this, and you're implementing something like a inner join that database normally would do inside, this bolt really needs to accept keys of the same value in the same instance. Otherwise, there would be no inner join that you can be certain of. All is a really special kind of grouping, and it's not so much about the data. What it means is that the copy of the tuple needs to go to all the instances of the downstream components. Why would you ever want that? Is because sometimes it's not so much about the data itself, but about the signal that something has happened. So if you want to reset cache on all of your 10 copies of the same bolt, well, you're going to send a signal to all of them, and that's the way to do it. Direct is a special case when you want to send, when the emitter of a tuple wants to send a tuple to a specific instance of a component. There is a bit of metadata information in the Storm that lets you see how many components are running for a given of a given type and what are their IDs. So theoretically, sender of a tuple could decide which component or which copy of the component given tuple is supposed to go. There are several more variations that are specifically targeting components running within JVM. There are optimizations on those same themes that JVM can do if you're running within the same process space. Now, what makes Storm interesting for .NET programmers is the fact that it implements something called Multiline Protocol. In addition to running Java components within JVM, where the Storm itself resides, it allows you to run out-of-process components. It's going to talk to them over std in, std out using JSON serialization, and it's going to instantiate a process for every instance of the component in your topology. Storm itself has several runtime components. Zookeeper, Java developers would be familiar with this. It's a runtime configuration and coordination service that's used across multiple Java projects. Nimbus. Nimbus is a management API for Storm. This is what you talk to when you want to find out what the state of your topology is. Supervisor. Supervisor is a process that runs your components. And the way Storm is designed, this is where most interesting stuff happens. Supervisors don't really talk to Nimbus for the management task or to carry out the transfer of tuples from one supervisor to another. They talk to each other. Storm UI is a little web-based interface that you'll see later that lets you see characteristics of your Storm cluster and the state of your topology. So in a nutshell, what is a Storm? Storm is a platform. It's a runtime. Instead of running applications directly on the operating system, you tell Storm to run it for you. And in exchange, what it does for you, it makes sure that everything is configured, because configuration is centrally done from Nimbus down to every component. It makes sure that all of them are running. If something has failed, it's going to restart it. It makes sure that your tuples are processed. If something has failed to process within certain timeout, the Storm is going to pick up that tuple and send it over again. So there is a caveat there that your handlers have to be idempotent. You have to be able to handle the same message twice.
And you have one supervisor per machine or core? How does it work?
Supervisor is per node. There's more abstractions to that. There's executor, for example. So how many threads within the supervisor are allocated to run your stuff. But we really don't need to know those details, at least not when you just want to try and see what ticks. And here's what that same thermostat topology would look like when implemented in Storm. As you can see, there's always almost one-for-one match there. So what are the details here? This number down here indicates how many instances I specified for this component to be in the topology when Storm starts it for me. So I have some queues that produce messages, and I have a spout that reads that message and emits that into the rest of my topology. I have 2 copies of writer bolt that takes what came in and writes into the database. 2 copies of projection that transforms the data for me. Passes it on to sensor view writer, where we aggregated the settings with the threshold and pass it on to notifier bolt. So if we need to send a message that we've triggered an alert to some other system, that's where it would end up.
So how do I know I need 2, or do you chose to have 2? How do you know?
The number is arbitrary, and the idea is that you would imagine what sort of workload this component would have, as well as what sort of parallelism you would benefit from. If it's a heavy task that would benefit from multiple parallel instances, well, you would increase parallelism. You would run it through your test environment to see if that's optimal configuration.
So they're completely redundant with respect to one another. You can put in 1, you can put in 5, and it'll just all come out in the wash.
That depends on the grouping. Remember I said that there's shuffle grouping and there is a field grouping. If I decide that it's important for me that same instance of the bolt receives the same keys, the same ID that it's going to serialize, then I could configure topology that way. Sorry, you had a question?
So suppose that the sensor writer gets an event, or
Yep.
I'm not sure. So how does it decide which of the instances gets the event or message?
Like I said, it's a configuration, and you will see the example later on how to configure that part. But essentially, it's your choice. If it doesn't matter to you which instance gets it, you leave it as default, and Storm will default to shuffle.
Oh, okay. Is that FIFO, like first come, first serve?
You know, I have no idea. I think we detected some sort of hashing, some sort of
You know how it distributes across
shuffle grouping.
yeah.
It's fairly random. There's probably some logic, but I don't know what it is. But for intents purposes, this is first come, first serve.
Okay, so
Can you do a load balancing?
A lot.
Say, you know, this task, the sensor view projection is a heavy duty thing, you know, do a lot of things.
Yeah.
For example,
Yeah, yeah.
load balancing on it.
Yeah, see, I specified that I want 2 instances, and I could say 10, and Storm will load balance it.
But do the Storm like a sense which one is busy and then you route the message to other idle, you know? Does it
Yes.
do automatically or?
Yes.
This is typically cluster configuration, right? You have
So, in terms of location, the configuration of Storm cluster itself and configuration of your topology are completely 2 different things. You could dynamically add machines to the Storm cluster, and Storm will redistribute the workload for you. Or one of your machines could die. This is the nature of distributed computing. What happens, Storm will notice that one of the supervisors is dead, and redistribute the workload in such a way that there is optimal number of components still running on the topology and keep serving the requests.
So all of this could be on a single machine?
It could be run on a single machine, which is what we're going to do. We're going to run this stuff on our laptops.
quick question. In terms of, since you've got the 2 sensor writers, messages can be delivered to them, and we don't really know which one of the 2 would be activated first, right?
So in terms of activated, they're active all the time. It's only a question of which one of them going to get it. And which one of them going to get it, we can either specify explicitly in the topology when we submit it. If we want certain ID to go to certain instance, we can enforce that. Or we can say it doesn't matter.
Okay, so the word activated was probably the wrong term. But let's say the supervisor's doing spout stuff at the moment, if my understanding is correct, and a message gets queued on sensor writer 0, and a message gets queued on sensor writer 1. There's a certain order in which these events happened. Is it important which one of the 2 is going to process this first? Like, especially since we're writer here, maybe I'm just stuck on the word writer because I'm imagining something writing to disk, and so the order in which things happen.
It's intentionally called writer because that's what it does. Except that directly going to disk, it writes to the database. But you're right, it's the same principle. So what would happen if we try to write something like that in SQL from multiple instances? Well, you may get 2 things. You may get a deadlock, or you may get stale exception, depending on which sort of versioning scheme your SQL server is configured for. That's why field grouping is critical, because you can say that all the updates pertaining to this ID should go through the same instance. This way, if you want to serialize your database access, you can.
Okay, that's how you enforce consistency.
Yeah. Some databases would not care, and they would happily carry out this update for you, and it's going to be peachy.
MySQL.
Yep. Yeah, for example, or Cassandra, which is what we're using. This is a meet, people. Let's talk.
How do you do redundancy? Is there any redundancy in here?
The redundancy is in the Storm cluster configuration.
How do you do persistence? What happens if something fails and the messages are midstream?
So how does Storm in general maintains the guarantees that something has been processed? Well, the tuples is just an obvious piece of what goes through all those streams. But the tuple is accompanied by metadata that says which stream this piece of information is supposed to go to, or which component this piece of information came from, as well as carry around acknowledgements. If Storm did not get acknowledgement for a bolt within given timeout, which you can configure, it's going to resend that tuple.
I
take it, because you were saying that persistence only happens at the start, like generally for tasks. If everything dies, the whole system goes down, and something is halfway through, I take it there is no recovery for that. So that is
Excellent question. So that comes to what is your spout and how is that implemented? We're using RabbitMQ, which allows us to acknowledge messages explicitly. If we didn't acknowledge it, it does not disappear from the queue. It sits there until the entire tuple tree has been processed.
When you say the tuples that are being passed between the components, you're saying you're building a tree out of them. Is it actually concatenating where it's been as it goes through the entire topology?
Yes, every new tuple has unique ID. So Storm internally maintains the tree of those IDs, which ones have been emitted from what, and whether or not they need to be anchored. So the only reason, the only scenario where entire tuple tree needs to be acknowledged to the spout is every single tuple that has been emitted from bolts has been anchored. If I did not anchor this emit here, the moment this bolt acknowledges that it has processed this tuple, even if it emitted something afterwards, the acknowledgement is going to arrive back to the spout, and what spout's going to do is going to go back to the RabbitMQ and say, this message has been processed, it's safe to delete. So processing guarantees are really in your hands. You want the entire thing to process before you acknowledge, you anchor every single tuple that you emit from your bolts.
I mean, all your arrows are facing this way, but there's actually quite a lot of information going backwards then as well.
Yes, the acknowledgements are going backwards, but your data only going forwards.
Yeah, yeah.
Is that on purpose? Is there no loops?
It has to be acyclic.
Sorry, it has what?
Acyclic.
Not cyclic.
This is
acyclic, okay.
yeah.
Not so.
Your messages always go like just one-to-one. There's no, like what if you want to be processed at the same time, multiple places, but only one to pass to the next point?
You can. If you remember the original Storm picture, there's multiple receivers of the same tuple. So essentially every one of them gets a copy.
That'd be the settings record there, right? It's altitudes.
Yeah, here. So the settings have been updated. We want to notify someone. The fact has been emitted on this stream and on that stream.
I guess I was thinking more from like a redundancy point of view. Is it try once, fail, try a different one, fail, try a different one, fail, or try to one succeed, abandon the other?
The thing is, you don't need to do that. Storm keeps those things alive for you. So you don't really need to retry it yourself.
But does Storm, like how does it manage that?
So the shuffle grouping will just try one after another. But the acknowledgements and another piece of metadata that Multilang implements is keep alive, essentially. So if your component did not report in a certain time, it's considered dead. Storm is going to restart it.
So then the messages have like a lifetime associated with them?
That's right. The entire tuple tree has a timeout.
And
Yeah.
So
Is that cool or what?
regarding the choice of parallelism,
Yep.
so at design time, you choose the parallelism based on what you think you need,
Yep.
based on your testing.
Yep.
It goes into production, you realize you didn't parallelize enough. You've got maybe one or two nodes there that you need more instances of. So can that be deployed to production seamlessly, or do you need to take the system down?
The system, right? Remember how we talked about availability? There is nothing immediately waiting for this processing to take place. And messages don't disappear. They just sit in the queue waiting to be processed. So you can safely kill the topology. You can safely kill your entire Storm cluster, and it's still going to be fine.
Just to comment on that, you can rebalance the nodes live and change the parallelism.
There you go.
Can you scale up live?
Yeah, so every time that gets more into the cluster configuration, which you mentioned earlier, which is completely separate from how this the bolts and spouts are handled. But you can add essentially supervisor nodes to your Storm cluster and then manually rebalance it. Technically, what it's doing is it's killing the topology and redistributing it across all of your nodes again. But it'll redistribute it automatically across all of them by defining how many executors you want to run it across. But you can also individually define per bolt and per spout if you want to essentially change the parallelism of each one live.
You talked about various other technologies. What is this bias that the other things?
It gives you near real-time processing. So with something like Hadoop, you don't get it. With something like Akka, you don't get this level of abstraction and supervision.
So is there anything that comes close, and what's the closest?
Spark streaming is the closest. Spark is primarily batching framework, but it can do micro-batching. And Storm is primarily event stream processing, which is one-on-one, but it can do micro-batching as well.
This actually looks a lot like Akka streams.
Yep.
So you'd have sources and you have sinks and
Right.
flows and stuff
Yep.
like that.
Can these different steps be... Well, I'm thinking now, it's again, my functional programming knowledge is a little rudimentary, but you can have these functions that you compose, right? So could these bolts be composed somehow? Is there any advantage in doing it that way? Like, let's say it's a series of little operations that get done really quickly. That kind of makes sense.
You're talking about stream fusion, I think.
Okay.
Like when you have many different components in the stream, they all get fused together and run on each message once.
The question is what exactly you're trying to get out of it.
Well, just
Because they are composed in the topology. They're running together. They're feeding data from one into another.
yeah. I guess it's the queuing, but I guess it doesn't.
Queuing.
Well, one element queue or a deeper one. Yeah, I guess it comes in on the same thing, really.
Yeah.
Yeah.
Yeah. It's queuing, but it doesn't hit the disk and maintains the delivery guarantees at the same time, which I think is pretty cool.
Can you prioritize some of the bolts? So instead of setting up daily events over there, I'm getting 1 million of them.
You just increase the number of those things that you want, which is what Dan was saying. If you want to change the parallelism of one of those bolts, you can.
But then you're forcing the limitation of the rest. It's basically the concept of there's a fire truck, so I have all the cars going, but if there's a fire truck coming, I want them to start getting down to the side. They all slow down, and then this one gets all the processing power.
So now we're getting into how big this topology is supposed to be. Because theoretically, there's nothing stopping you from breaking down your big problem into smaller chunks and processing them in separate topologies.
So, well, the concept is you don't need to go faster than a line if there's no line. But that's only if you have enough processing power to process them fast enough.
The back pressure would help there. So basically, if you're saying that my topology cannot keep up with the amount of messaging coming in, you could specify the back pressure.
You have back pressure in Storm?
Yes. You can say that I don't want to see no more than 100 unacknowledged messages from this spout. And if you have broken down your problem solving into multiple topologies, you have a degree of control how fast each of them processes the messages.
So you can say, don't send me more than 5 events right now. And then later you can say, send me 100 events.
So the bolt has some capability like a TCP/IP sliding window, right? So that the receiver end can tell the sender, don't send me, too fast. I cannot process.
Except that this parameter is per topology. It's not per bolt.
Sometimes you can't really
limit that too much either. If you've got plenty of users making updates, or something like that, you can't really just stop it.
I think the important characteristic is keeping your system working at optimal level. So you would do some performance testing ideally and find out what the optimal number of unacknowledged messages is.
All these things, it always seems to boil down to you need to just make it big enough or at least scalable enough or adaptable enough to handle the load. Kind of like the situation there where you're saying everybody has to do all of the fire truck. Well, your road was obviously not big enough for the application. Like a bigger road. Not these computers, you can do that, I guess. Does that make sense? Or?
Yep.
How does it talk between bolts? Like
There is a Multiline Protocol that FS Storm implements.
like on machine and between like network and
Internally, Storm cluster uses Netty. Or sorry, Jetty. I'm confused. I'm not in the Java land. So there is some high-performance protocol that supervisors use to talk to each other and to Nimbus. So FS Storm. When I started looking at Storm, I came across Microsoft implementation, which is implemented in C#. And verbosity of that thing is atrocious, as well as the API that it offers to you. So I kept looking, and I came across FS Storm, which was open source just a month prior. And it looked amazing. So you get strongly typed DSL in F#, where you define your topologies. You get runtime that implements Multilang. So all you have to do is define your components. And components can be one line of F#. Added later on the implementations and broken up things a little bit more so that you could unit test your components, because that was our #1 challenge when we started with it. Well, how do you test it? You have to submit, and once you submit it, like, okay, what went wrong? So adding some test components into the library helped. We can test our every one of our bolts and spouts in isolation and make sure that they behave the way that we want them to behave. The topology is validated for you. So if you're trying to insert an invalid reference to a spout that doesn't exist, the validation will make sure that it doesn't happen. It will. The moment you try to submit that topology, it will tell you, there's a problem here.
Will it get cycles?
Have to try that. Don't know. Scripts, and supplies a small library of scripts that help you submit to Nimbus. Normally you would use Storm Java runtime for that. There's nice enough code base that lets you just talk to Thrift API on the Nimbus directly without needing a Java runtime. So you can live entirely in .NET space. Justin will show you an example, exciting example, word count. Any questions before I move to that? Anyone want to play along? You could download the code and do it yourself, no?
So, sorry, when you mentioned that you don't have to go into the Java land, you submit your topology to Nimbus. What is Nimbus exactly?
Nimbus is a management API, essentially, for submitting topologies into Storm cluster, or killing them, or finding out how they're doing.
But it does run a JVM, right?
That's right.
Okay.
It exposes Thrift API, however, so theoretically you have no need to have Java on your client side.
Okay.
So any way to communicate across the bulk?
That would be in the spouts and bolts of your topologies. So using the Storm facilities only, probably not. There is one exception, however. Out of the box, Storm comes with implementation of spouts and bolts for Kafka. So if you have Kafka in your runtime environment, you could configure the edge points for topologies to talk to each other through fast Kafka implementation. Another runtime that you could use for that is InMemory message queue that I believe is also packaged with Storm. So there's a delivery guarantee right there in memory.
So I missed the idea of why did you move to F#?
because for usual reasons why anyone moves to F#, right? It's about 10% of your code base, and it's really expressive. So looking at C#, I see a lot of superficial types. I see strings passed all around. I see Java runtime that you need in order to submit topology. And most upsetting was that you only could work with Azure Storm implementation. You couldn't run your own Storm clusters.
Okay, so it's for compatibility with Azure.
Yep. So, practical example?
So the initial Storm you showed us isn't necessarily functional. It could be any other language. Maybe in this case it was Java.
Yeah, so Multilang lets you program in any language because serialization is overstood in, listed out. You could write C++ components.
Right.
And people probably have.
But the whole thing is implemented in Clojure.
The whole thing, the core of Storm is implemented in Clojure, but there's a lot of Java plumbing around it. It runs within JVM, obviously.